Welcome back. Last episode, we built the convergence toolkit, 7 tests for deciding whether an infinite sum converges. Today, we put that toolkit to its greatest use. Here is the central object of this episode. The Taylor series of a smooth function, f at a point a, is the infinite sum of the nth derivative of f at a over n factorial times the quantity x minus a to the n, running from n equals 0 to infinity. When a equals 0, this gets a special name, Maclaurin series, and the formula simplifies because all the x minus a factors become just x. The whole episode unpacks one idea. Back in episode 10, we did linear approximation, replace f near a by the line f of a plus f prime of a times the quantity x minus a. That matched f's value and first derivative at a. Today we ask the obvious next question. What if we also match the second derivative, the third, the fourth, the nth? The answer is unique. There is exactly one infinite polynomial whose derivatives at a agree with f's derivatives at a to all orders, and its coefficients are the nth derivative of f at a over n factorial. That polynomial is the Taylor series. We'll derive the famous ones, e to the x, sine x, cosine x, 1 over 1 minus x, the natural log of 1 plus x, use them to compute things like e to the 0.1 by hand, and meet Taylor's remainder theorem, which tells us exactly how good these approximations are. Let's go! Before we write down the Taylor series, let's retrace the idea, starting from where we left off in episode 10. Back then, we used the linear approximation. Near a point a, the function f is approximately f of a plus f prime of a times the quantity x minus a. I'll call this p sub 1 the polynomial of degree 1. Why does p sub 1 work as an approximation? Because it matches f in two ways at a. First, p sub 1 of a equals f of a, same value. Second, p sub 1 prime of a equals f prime of a d sub prime of a, same slope. We have a polynomial of degree 1 that agrees with f on the first two derivatives, the 0th and first. Here is the natural question. Why stop at p sub 1? Why match only the 0th and first derivatives? What if we demand a polynomial p sub n of degree n such that the kth derivative of p sub n at a equals the kth derivative of f at a for every k from 0 to n? That is, what if the polynomial agrees with f on all derivatives up to order n at the point a? Two questions. Does such a polynomial exist? Is it unique? And what are its coefficients? Let's find out. The answer falls out of one page of algebra. Time for the derivation. Suppose such a polynomial p sub n exists. Write it in powers of x minus a, p sub n of x equals c sub 0 plus c sub 1 times the quantity x minus a, plus c sub 2 times the quantity x minus a squared, and so on up to c sub n times the quantity x minus a to the n. The coefficients c sub k are what we want to find. Differentiate k times. Each term c sub j times the quantity x minus a to the j, when differentiated k times, contributes c sub j times j minus 1 times j minus 2, and so on, down to j minus k plus 1 times the quantity x minus a to the j minus k if j is greater than or equal to k, and 0 otherwise. Now plug in x equals a. Every term with x minus a to a positive power dies. Only the term with j equals k survives, and it contributes c sub k times k minus 1 times k minus 2, and so on, down to 1, which is k factorial times c sub k. So the kth derivative of p sub n at a equals k factorial times c sub k. We demanded the kth derivative of p sub n at a equals the kth derivative of f at a. Equate, solve, c sub k equals the kth derivative of f at a over k factorial. One formula. Every coefficient determined. That gives us the Taylor polynomial of order n at the point a, p sub n of x equals the sum from k equals 0 to n of the kth derivative of f at a over k factorial times the quantity x minus a to the k. Existence, this formula constructs it. Uniqueness, the matching conditions pin down every c sub k. There is no ambiguity. The polynomial is determined. Now take the limit as n approaches infinity. The Taylor series of a smooth function f at a is the infinite sum of the nth derivative of f at a over n factorial times the quantity x minus a to the n. That's the box. Memorize it. Notation. If a equals 0, we drop the a and write the sum of the nth derivative of f at 0 over n factorial times x to the n. This case is called the Maclaurin series, named after Colin Maclaurin, the 18th century Scottish mathematician who popularized it. Most of the famous series we'll see today are Maclaurin series. Expanding at a equals 0 is almost always the cleanest choice. Two caveats before we play with examples. First, the series might not converge for every x. Convergence depends on the function and the point. The geometric series for 1 over 1 minus x only converges for the absolute value of x less than 1, for instance. We'll see why. Next episode is dedicated to this question, the radius of convergence of a power series. Second, and more subtly, even when the series converges, it might not equal f of x. There exist smooth functions whose Taylor series at a point converges, but to the wrong value. Pathological, but real. Taylor's theorem with remainder gives us a tool to prove equality for the standard examples. We'll get to that in a few slides. For now, the standard transcendental functions, e to the x, sine x, cosine x, the natural log of 1 plus x, all play nicely. Their Taylor series at reasonable points converge and equal them. Let's compute. First example, the cleanest possible. Find the Maclaurin series of e to the x, compute the derivatives, f of x equals e to the x, f prime of x equals e to the x, f double prime of x equals e to the x. By induction, the nth derivative of f of x equals e to the x for every n. The exponential is its own derivative, the property that defines it. Evaluate at 0. The nth derivative of f at 0 equals e to the 0, which is 1. Every single derivative at 0 equals 1. The coefficients, the nth derivative of f at 0 over n factorial, are just 1 over n factorial. Plug into the Maclaurin formula, e to the x equals the sum from n equals 0 to infinity of x to the n over n factorial. That's the series, spell it out. E to the x equals 1 plus x squared over 2, plus x cubed over 6, plus x to the 4th over 24, plus x to the 5th over 120, and so on. The factorials in the denominator grow ferociously. 5 factorial is 1/1020, 10 factorial is about 3.6 million, which is why this series converges for every real x and even every complex x. Use the ratio test. The absolute value of a sub n plus 1 over a sub n equals the absolute value of x over n plus 1, which approaches 0, less than 1, for any fixed x. By episode 13's ratio test, converges absolutely, always, and it equals e to the x. Why? Because e to the x is analytic in the strongest possible sense. We'll prove equality via the remainder theorem shortly. But intuitively, e to the x is the unique function that equals its own derivative and its own value at 0, and the series has the same property. They're forced to coincide. This is the cleanest series in all of mathematics. Second example, Maclaurin series of sine x. Differentiate, f of x equals sine x, f prime of x equals cosine x, f double prime of x equals minus sine x, f triple prime of x equals minus cosine x. The fourth derivative of f of x equals sine x. We're back where we started. The derivatives cycle with period 4, sine, cosine, minus cosine, sine, cosine, and so on. Evaluate at 0. Sine of 0 equals 0, cosine of 0 equals 1, minus sine of 0 equals 0, minus cosine of 0 equals minus 1. Cycle 0, 1, 0, minus 1, and so on. Every even index derivative gives 0, which kills the even powers in the series. Every odd index derivative gives plus or minus 1, alternating in sign. Plug in. The coefficient of x to the 2n plus 1 is negative 1 to the n, over the quantity 2n plus 1 factorial. So sine x equals x minus x cubed over 6, plus x to the 5th over 120, minus x to the 7th over 5040, and so on. Compactly, the sum of negative 1 to the n times x to the 2n plus 1 over the quantity 2n plus 1 factorial. Features. Only odd powers, because sine is an odd function. Sines alternate, courtesy of cosine and minus sine cycling. Denominators are odd factorials, which again grow fast enough that the series converges for every real x and every complex x. Same ratio test argument as e to the x. Notice the elegant family resemblance to the e to the x series. They both involve factorials, they're both convergent everywhere, they're both fundamental. In fact, with complex numbers and Euler's formula, e to the ix equals cosine x plus I sine x ties them together explicitly, but that's a story for another episode. Third example. Maclaurin series of cosine x. 2 ways to derive it. The slick way, just differentiate the sine series term by term. Cosine x equals the derivative with respect to x of sine x. Take the series for sine x, differentiate every term. X becomes 1, minus x cubed over 6 becomes minus x squared over 2. X to the 5th over 120 becomes x to the 4th over 24. Pattern, cosine x equals 1 minus x squared over 2, plus x to the 4th over 24, minus x to the 6th over 720, and so on. The direct way, compute the nth derivative of f at 0 for f equals cosine. Derivative cycle cosine, minus cosine, sine, cosine, and so on, evaluated at 0 gives 1, 0, minus 1, 0, 1, 0, minus 1, 0, and so on. Now even derivatives survive, giving even powers in the series, and odd derivatives die. Signs alternate. Same result. Pretty form, cosine x equals the sum of negative 1 to the n times x to the 2n over the quantity 2n factorial. Only even powers, because cosine is an even function. Alternating signs. Even factorials in the denominator. Sine and cosine are complementary. Sine has odd powers and odd factorials. Cosine has even powers and even factorials. Together they partition the Taylor series of the complex exponential. Add them. Cosine x plus I sine x equals the sum of ix to the n over n factorial, which equals e to the ix. Euler's formula drops out of one line of bookkeeping. Magic hiding in plain sight. Fourth example, Maclaurin series of 1 over 1 minus x. This one we sort of already have. The geometric series, the sum of x to the n, equals 1 plus x squared plus x cubed, and so on, equals 1 over 1 minus x when the absolute value of x is less than 1. That's the geometric series formula from episode 12. Diverges for the absolute value of x greater than or equal to 1, because the terms don't go to 0. Let's verify it as a Maclaurin series. Compute derivatives of 1 over 1 minus x. The first derivative is 1 over the quantity 1 minus x squared. The second is 2 over the quantity 1 minus x cubed. The third is 6 over the quantity 1 minus x to the fourth. Pattern, the nth derivative of f of x equals n factorial over the quantity 1 minus x to the n plus 1. Evaluate at 0, the nth derivative of f at 0 equals n factorial. Plug into the Maclaurin formula, the coefficient of x to the n is n factorial over n factorial, which is 1. The series is the sum of x to the n, confirms the geometric series formula. Two things to notice. First, the geometric series is the Maclaurin series of 1 over 1 minus x. Now you know why it shows up so often. It's the Taylor expansion of a fundamental rational function. Second, this is the first series we've met that doesn't converge for all x. The function 1 over 1 minus x has a pole at x equals 1. The Taylor series can't see past that pole. Its radius of convergence is 1, the distance from the expansion point 0 to the nearest singularity. That's a sneak peek at next episode. Fifth example, Maclaurin series of the natural log of 1 plus x. We could grind out the derivatives at 0, and it works, but there's a slicker route. Start from the geometric series and play. Replace x with minus x. 1 over 1 plus x equals 1 minus x plus x squared minus x cubed, and so on, valid for the absolute value of x less than 1. Now integrate both sides from 0 to x. On the left, the integral from 0 to x of dt over 1 plus t equals the natural log of 1 plus x minus the natural log of 1, which equals the natural log of 1 plus x. On the right, integrate term by term, x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, and so on. Result. The natural log of 1 plus x equals x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, and so on, equals the sum of negative 1 to the n plus 1 times x to the n over n, starting from n equals 1. Where is this valid? At least for the absolute value of x less than 1, since that's where the geometric series we integrated converges. But it also turns out to converge at x equals 1 by the alternating series test. The terms negative 1 to the n plus 1 over n are alternating and shrinking to 0. Plug in x equals 1, and you get the natural log of 2 equals 1 minus 1 half plus 1/3 minus 1/4, and so on. The alternating harmonic series we met last episode. So the alternating harmonic series equals the natural log of 2 about 0.693. Now we know exactly why, and we've earned that fact. At x equals minus 1, the series becomes minus 1 minus 1 half minus 1/3 minus 1/4, and so on, which is minus the sum of 1 over n, the negative harmonic series, which diverges. Matches the fact that the natural log of 1 plus x approaches minus infinity as x approaches minus 1 from above. Picture this. Here is sine x in blue, and its Taylor polynomials p sub 1, p sub 3, p sub 5, p sub 7 at a equals 0 in dashed colors. P sub 1 of x equals x, the linear approximation. It hugs sine x very near the origin, then peels off as sine x starts to curve. P sub 3 of x equals x minus x cubed over 6. Track sine x through the first peak around x equals pi over 2, then shoots off to negative infinity as x cubed dominates. P sub 5 of x equals x minus x cubed over 6 plus x to the fifth over 120. Tracks through the trough at x equals minus pi over 2 as well. Follows sine x further before the x to the fifth term takes over. P sub 7 of x equals x minus x cubed over 6 plus x to the fifth over 120 minus x to the seventh over 5040. Track sine x across nearly the whole window, good agreement through about the absolute value of x less than 4. Pattern. Each additional term extends the range over which the polynomial follows the function. As n approaches infinity, the Taylor polynomial p sub n converges to sine x for every real x. That's what it means to say the Taylor series of sine x has infinite radius of convergence. No matter how far from 0 you are, going to high enough degree eventually catches you up. This picture is the whole episode in one figure. A smooth function is, in this precise sense, the limit of its polynomial approximations. Time to make this concrete. Approximate e to the 0.1 using the Maclaurin series we just derived. Plug x equals 0.1 into e to the x equals the sum of x to the n over n factorial. The terms are 1, then 0.1, then 0.1 squared over 2 factorial, which is 0.005, then 0.1 cubed over 3 factorial, which is 0.001 over 6, about 0.000167, then 0.1 to the 4th over 4 factorial, which is 0.0001 over 24, about 0.000042, and they keep shrinking. Add up the first 5 terms. 1 plus 0.1 plus 0.05 plus 0.0000167 plus 0.0000042, which is about 1.105171. Done. By hand. No calculator needed for any of the arithmetic. Now compare to the actual value. E to the 0.1 from a calculator, 1.105170910808, and so on. Our estimate, from 4 non-zero corrections to the leading one, agrees to 6 decimal places. That is wild. The polynomial of degree 4 already nails e to the 0.1 to 6 places. Why does it work so well? Because x equals 0.1 is small, and the next term, 0.1 to the 5th over 120, about 8.3 times 10 to the minus 8, is the bound on the error. Tiny x means tiny powers of x means tiny tail. The series converges fast for x close to 0. Further from 0, you need more terms. To compute e to the 10 to 6 decimal places, you'd need a lot more. But for small x, Taylor series are the fastest game in town for transcendental functions. This is, by the way, exactly how your calculator computes e to the x internally. It doesn't have a magic e function chip. It runs a few terms of the Taylor series. Now the theoretical backbone. Taylor's theorem with remainder. Statement. If f is n plus 1 times differentiable, then f of x exactly equals p sub n of x plus a remainder term r sub n of x, where the remainder has a clean form. Lagrange's form, r sub n of x equals the n plus first derivative of f at xi over the quantity n plus 1 factorial times the quantity x minus a to the n plus 1 for some xi between a and x. Looks like the next term of the Taylor series, except the derivative is evaluated at some intermediate point xi rather than at a. In practice, you use the bound. Take m sub n plus 1 to be the maximum of the absolute value of the n plus first derivative of f on the interval. Then the absolute value of r sub n of x is at most m sub n plus 1 over the quantity n plus 1 factorial times the absolute value of x minus a to the n plus 1. Why does this matter? The series equals the function exactly when the remainder goes to 0 as n approaches infinity. Symbolically, f of x equals the sum of the nth derivative of f at a over n factorial times the quantity x minus a to the n if and only if r sub n of x approaches 0. Apply to e to the x. The derivatives of e to the x are bounded by e to the absolute value of x, a finite constant for fixed x. So the absolute value of r sub n of x is less than or equal to e to the absolute value of x times the absolute value of x to the n plus 1 over the quantity n plus 1 factorial, which tends to 0 for any fixed x, because n plus 1 factorial outpaces any exponential. So e to the x equals its Taylor series for every real x. Same argument for sine and cosine. Derivatives are bounded by 1, factorial in the denominator wins. Equality for every real x. That's the rigor we needed. Taylor's theorem with remainder is what makes Taylor series more than formal manipulation. It tells you by how much the polynomial differs from the function, and it tells you exactly when at different sti's. Quick historical detour. Like much of calculus, the Taylor series wasn't really invented by Taylor. The earliest documented power series expansions of trigonometric functions come from Madhava of Sangamagrama and the Kerala school of astronomy in 14th century India. They had Maclaurin series for sine and cosine and arctangent, 2.5 centuries before European calculus existed. They used these expansions to compute pi to very high precision and to study planetary motion. This work was largely unknown to European mathematicians at the time. James Gregory rediscovered the arctangent series in 1671. Newton developed extensive power series expansions in his 1665 work on infinitesimal analysis, including the generalized binomial series, which gave him Maclaurin expansions of many algebraic and transcendental functions. Brooke Taylor's contribution, in his 1715 Methodus Incrementorum, was the general formula at an arbitrary expansion point a, the one we now write as the sum of the nth derivative of f at a over n factorial times the quantity x minus a to the n. He did not, however, address convergence. Colin Maclaurin's 1742 treatise of fluxions popularized the a equals 0 case, which is computationally easier and is the one students meet first. Convergence and the remainder theorem came from Lagrange and Cauchy in the late 18th and early 19th centuries, 100 years after Taylor. Like much of calculus, the rigorous foundations lagged the formal manipulations by generations. Recap. The Taylor polynomial of order n is the unique polynomial of degree at most n whose derivatives at a agree with f's derivatives at a up to order n. Its coefficients are the k-th derivative of f at a over k factorial. Let n go to infinity and you get the Taylor series. When the expansion point is a equals 0, it's called the Maclaurin series. The famous Maclaurin expansions, valid for all real x e to the x equals the sum of x to the n over n factorial. Sine x equals the sum of negative 1 to the n times x to the 2n plus 1 over the quantity 2n plus 1 factorial. Cosine x equals the sum of negative 1 to the n times x to the 2n over the quantity 2n factorial. Plus the geometric series, 1 over 1 minus x equals the sum of x to the n for the absolute value of x less than 1, and the natural log of 1 plus x equals the sum of negative 1 to the n plus 1 times x to the n over n for the absolute value of x less than 1. Extending to x equals 1 by the alternating series test. Worked example, e to the 0.1 from 4 non-zero terms gives 1.105171, matching the truth to 6 decimals. This is essentially how calculators compute exponentials and trig functions. Taylor's theorem with remainder closes the loop. F of x equals p sub n of x plus r sub n of x, with the remainder bounded by m sub n plus 1 times the absolute value of x minus a to the n plus 1 over the quantity n plus 1 factorial. When r sub n approaches 0, the series equals the function. For e to the x, sine x, cosine x, that happens everywhere, courtesy of the factorial in the denominator outracing every exponential. Next episode, we formalize where a general power series converges. Radius of convergence, interval of convergence. See you there. That's Taylor and Maclaurin series. The recipe, the nth derivative of f at a over n factorial, turns every smooth function into an infinite polynomial. The standard transcendentals, e to the x, sine x, cosine x, the natural log of 1 plus x all yield to one calculation. Taylor's remainder tells us how close the truncation is. If this helped, like, subscribe, drop a comment. Tell me your favorite Maclaurin series, or one whose convergence behavior surprised you. Next episode, power series and the radius of convergence. We've seen that the Taylor series for 1 over 1 minus x converges only when the absolute value of x is less than 1, while the Taylor series for e to the x converges everywhere. Why? We'll prove that every power series has a number r, the radius of convergence, such that the series converges for the absolute value of x minus a less than r, and diverges for the absolute value of x minus a greater than r. And we'll compute r for every series we've met today. See you there. Taylor and Maclaurin series are the bridge from calculus to the rest of mathematics. We started from linear approximation in episode 10. F of x is approximately f of a plus f prime of ax minus a, and notice the obvious question: what if we match not just the first derivative at a, but the second, the third, the nth? The answer, the Taylor series, is the unique polynomial whose derivatives at a agree with ff's derivatives at a to all orders. The coefficients fall out algebraically, f to the of n a n. When a equals 0, the series is named after Maclaurin, and computation becomes easy. We derived the famous expansions, e to the x, sine x, cosine x, 1 minus x, the natural log of 1 plus x, saw how to compute e to the 0.1 by hand to 5 places, and met Taylor's theorem with its remainder bound, which tells you exactly how good the polynomial approximation is. Next episode, we ask the natural follow-up. A Taylor series is a special case of a power series, the sum Cn of x minus a to the n, and these have a precise radius of convergence, r, the interval around where the series actually equals the function. We'll compute r for each of today's series, see why the natural log of 1 plus x stops working at x equals minus 1, and uncover the strange case where f is smooth but its Taylor series diverges everywhere. Subscribe and you won't miss it. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.